All right, thanks everyone for coming. Thanks to Garrett and the Chicago ML Meetup for having me. My name is Greg Gandenberger, pronouns he, him, his. I'm a data scientist at ShopRunner. I'm going to talk about managing deep learning projects, but I'm not going to talk about the deep learning itself. I'm going to talk about managing all of the other stuff that you have to keep track of as part of a machine learning project. So I'm going to do it in four buckets. So the first bucket is ideas for helping you manage your data, then managing code, managing dependencies, and managing experiments. A lot of what I'm going to say applies to any kind of machine learning project, but some of it is specifically particularly relevant to a typical deep learning project. So for instance, with data, you always have to manage data for any kind of machine learning project, but for a deep learning project, you often have a lot more data and it might be spread across a bunch of files. And so the problems I'm addressing are particularly challenging for a typical deep learning project. Throughout the talk, I will refer to this example project. So this project is called Autofocus. It's an open source machine learning project hosted by Uptake that I've worked on. It's a collaboration with the Lincoln Park Zoo's Urban Wildlife Institute. They have deployed dozens of motion activated cameras around Chicago. And the idea is that these cameras will take pictures of animals. Those pictures get uploaded to a crowdsourced website where people will identify the animals that they contain. So like this one has a coyote. The researchers want to avoid as much as possible posting images that have humans in them, just to try to protect people's privacy. And so the first version of this model classifies images to say, yes or no, does this have a human in it? And so that allows them to eliminate a lot of the images they don't want to post right off the bat. We're also working toward better support for automatically doing all of the classification. So this is open source, it's on GitHub. Definitely if anybody's interested, check it out and we'd love to get contributions. Okay, so now getting into the content. First, I'm going to talk about ideas for managing data. So one challenge, again, with deep learning projects in particular is that they often involve large collections of files. For autofocus, for instance, we have about 150,000 images. Processing these files and moving them around can take a very long time, even before you start doing deep learning. So some examples of things you might need to do. The images live on S3. You'll need to download them to wherever you're going to work on them. Just downloading 150,000 images can take like a day. A lot of these images have a strip along the bottom with some metadata. I suspect that metadata will only mess up a model, that the model will use it to cheat and to figure out something about like the location, and that stuff won't generalize. So I suspect we're best off trimming away that metadata. The images are like 1,500 pixels on the side, some of them, which is way bigger than necessary. So we want to resize them to be, so I've made them 512 pixels on the longer side, which is plenty for standard deep learning image classifier. And if we resize them just once up front, then that saves storage and processing time while we're training the model. Also, some of these images are taken at night using an infrared sensor, which means that they're grayscale. Others are taken during the day using a standard camera, so they're color. So it may be that the best thing to do is to have one model that handles all the images, or it may be that you'd be better off having one model for the grayscale and one model for the color. We'd want to be able to experiment with both. So in processing these 150,000 images, we need to open them up and see how many channels they have and record which ones are grayscale and which ones are color, so we can do different experiments using that information. Okay, so there's a lot of stuff we want to do with these images. Just loading them and saving them already can take many hours. If I change my mind about what I want to do, like maybe I don't want to trim the bottoms after all, then I've got to do the process all over again. Almost inevitably, when you have this much data, some of it's going to be corrupted. So you can have a run where you're processing and downloading all these images, and then you get a third of the way through and you get an error and it all stops. And also you want to keep track of what you've done, so which files you processed in what ways. And so this can all be very time consuming and it's not very fun. You just want to get to building the model. So how can we deal with these challenges? Well, one thing that can be a big win is instead of processing the images serially one after the other, you can have some parallelization. Can reduce the amount of time for this processing by about an order of magnitude. The most expensive steps are just opening the images and then writing them, and that's easily parallelized across threads. Another thing you'll want to do is do all operations in one pass. So when I first started on this project, I downloaded all of the images, and then I trimmed the bottoms off all of the images, and then I resized all of the images. And so I was opening and saving the images 3 different times. And again, those IO operations are the bulk of the work. So that's a very inefficient approach. It's much better to, even when you're downloading the image, you grab the image data, do all of your operations once, and then you write out the result. So that'll save a lot of time. You also need to handle errors from corrupted data. So you won't necessarily know what they'll be up front, but after a run or two, you'll know what kinds of errors tend to come up. And you can do like a try except to catch those errors. If your run does fail, say a third of the way through, you'd like to be able to pick up where you left off. So you want to skip files like input files where you've already written the output. So you can check, have I already written the output for this thing? And if so, you want to skip that so then you can pretty much pick up where you left off. And you also want to keep organized records of everything, including like, let's say this file was already there, so we skipped it. We want to record that. We want to record any files that gave us an error. For files that we did write, we want to record where we wrote them to. And in this case, we want to record which ones are grayscale and which ones are color. So we want to keep organized records of all of that. Problem is, this is an awful lot of stuff to do. None of it's trivial. And if you're not sort of thoughtful about how you write your code, you can end up doing these very same things for project after project. Don't worry, we got you. So ShopRunner has an open source library called Creevey that handles all of this junk for you. So you don't have to spend obscene amounts of time writing code that parallelizes your processing steps and handles all these errors for you. You can just use our library. So I said you want to parallelize your operations. Creevey will do that for you. You just tell it how many threads you want. Said you want to do everything in one pass. Creevey will do that for you. You just pass in a sequence of functions you want to apply, and Creevey will pipe each of your input files through that sequence of functions. Once you know what error types you want to catch, you just specify those error types, and Creevey will like do the try except and handle them. If you want it to, it'll skip any files that already exist and just move to ones that aren't already there. Or you can tell it, don't do that, and then it will overwrite any existing files. And in the end, it gives you back a report of what happened. So it'll tell you for each file, was it skipped? Was there an error? Or if not, where did we write it to? And it'll also record other stuff that you ask it to record, like was this image grayscale or color? That's not all. Creevey does. There's more than that to Creevey. So Creevey also, in addition to the overall framework, it has predefined pipelines and functions specific to image processing. So you can just import and use these predefined functions to load an image from a URL or from a file path, to write it to disk in the end, to record properties of the image, like its brightness, is it grayscale or color, and to do various kinds of transformations like padding or cropping or resizing. But wait, there's not more, but there could be. We'd love to get contributions, including, so for the image operations, we've just been adding stuff as we go, as we need it for our projects. There are lots of other image processing operations that could be added. Also, the framework is not specific to images. It would work just as well for text, audio, video, any big collection of files you want to process. We just don't have any predefined components for that stuff. So if anybody has projects using this kind of data and they'd like to use creevey, we'd love to have contributions for like predefined pipelines and functions that would work for those data types.
Greg, how does, is there a crawling function? I mean, maybe you mentioned that, I missed it. How does creevey acquire these images and know where to look for them and how to crawl different sources?
That's an input. So you need to pass in a sequence, like a list of URLs or paths.
Got it.
So creevey does not handle that. There might also be possibilities for adding new capabilities to creevey, adding new features to the framework. Yeah, so we love to get contributions for anyone who's interested. Feel free, like Garrett, to jump in with questions at any point, by the way. So let me show you what some code that uses creevey looks like. So this will take us to the actual file processing code that I wrote for autofocus. This custom reporting pipeline so pipelines are like the central abstraction for creevey. So when you create a pipeline, you pass it a function that tells it how to load a single file. So in this case, I'm using a predefined creevey function to load an image from disk. So this is a function that takes a path on disk and loads in the image data. And then you pass in a sequence of operations to apply to the image. In this case, we're first trimming that footer. So it's like that bottom 100 pixels or something like that. Then resizing it so that it's, I always say this wrong, its smaller dimension is 512. So I'm being conservative. So it's wider than it is tall. It'll end up 512 pixels tall in this case. And then we have, so those are both transforming the image, those functions. And then we have two functions that are recording information about the image, whether or not it's grayscale, and then its mean brightness. Some of the images are real washed out. I think it happens around like dawn and nightfall when it switches to the infrared sensor, but there's still some sun out. You get really washed out images. So I want to record the mean brightness and then maybe throw away some that are all pretty much all white. So we tell the pipeline again how to load in a file, the sequence of functions to pass that file through, and then how to write it out. So in this case, we're just writing the image to a path on disk. So that's defining the pipeline, and then the pipeline has a run method. At runtime, you give it a sequence of paths, which will be then passed to your load function. So this is like our sequence of image URLs. We load each one in and then process it. You give it a function that tells it how to derive an output path from each input path. So in this case, all I'm doing is changing the directory. So I think actually in this case, I'm starting with images on disk. So they're in a like data/raw, and I swap out the directory so they go to data/processed. So that's what path function says. So it takes an input path and gives you an output path. Tell it how many threads to use. In this case, I'm not skipping existing, so we'll overwrite any files that are already there. I found that sometimes I get a 0 division error for bad data, so we catch that exception. And that's it. And in the end, it does all of this processing and writing out the images, and it returns a data frame, which is this report of what happened. So here's an example. You've got the input paths in the index, and then the corresponding output paths. 0 or 1, did it skip this file because the output path already existed? Did it handle an exception for this file? And then in this case, I asked it to tell me, is this image grayscale or not? Okay, so that's creevey. Any questions at this point?
Yeah, Greg, I have one. and this might be kind of dumb because you're saying you're reading it from disk. Are you meaning that you were able to do this all like locally, or were you reading, like doing all the processing from like an EC2 or something like that?
Both. So creevey can do either. You just have to give it an appropriate function that when you give it in, you pass in an input path, and the function knows how to load in the data from that input path and return like the image. So all my image functions use NumPy arrays. So it would return the image as a 2D array, and then it passes it on to the next function. Yeah, so like there's a function in creevey, load image from URL, so you can pass in URLs, or load image from disk, I think it's called, and you can pass it in paths to local files.
Got it.
Okay, so that's our solution to this problem of having to process lots of files, maybe multiple times. We have creevey handle the annoying bits. Another problem when you're dealing with data can be that different people like to store data in different places. So I like to put it on so I'm working on an AWS on an EC2 instance. I like to put the data on a mounted volume, which I can move around and attach to different instances. I can also throw it away when I'm done without affecting my instance. Other people like to have all of their data in one place in like a centralized data directory, so that when their hard drive fills up, they know where to go to start deleting things. Still other people like to have a data directory inside the repository, like Driven Data has a template where they suggest that approach. So when you're collaborating with people who have different preferences, you need to find some way to get along. So there are a couple unsatisfactory solutions. One is to just be opinionated, say, you know, well, I like to have it on a mounted volume, so that's what we're going to do. The advantage of this approach is if the data is if you know the data is in a particular place, all of your code can refer to that location. And that just simplifies a lot of the code. The downside, of course, is that you might annoy other people. Another unsatisfactory solution is have all of your code like ask where the data lives. So like all of your scripts have a parameter, which is like, where's the data? And the annoying thing about that is just that you end up with these really long script calls where like every time you do anything, you've got extra arguments that are kind of cumbersome. So here's a better solution. I like to use an environment variable for each project. So like for autofocus, the README has you create an environment variable for your autofocus data that specifies where you want to store it. And that can be anywhere you want. It can be on a mounted volume. It can be a centralized data directory, whatever. And then in the code, we can just refer to this environment variable. So we kind of get the best of both worlds where all of our code knows where the data lives in terms of this environment variable, but where that variable points is up to the user. A couple of additional tips for managing your data. One is to use Parquet or Feather rather than CSV. That'll preserve your column types. So at ShopRunner, we have a data set where each row is a product. So we work with a lot of fashion retailers. So like a particular row might be a dress. One of our columns is image URLs for that product. So that column will have a list of a bunch of image URLs for that dress. But the annoying thing is if you write that data to CSV and then you read it back in, it gets read back in as a string that looks like a list, but it's not actually a list. You don't have that problem if you use Parquet or Feather. Finally, there's a library called S3FS. If you have that installed, then pandas can pull data from S3 and write it to S3 directly. So you can just use S3 paths like this, and it just saves you a step and some disk storage because you don't have to write the data to disk and then read it from disk. All right, that's what I have on managing data. Any questions at this point?
Nope.
We'll move on to code then. So I've struggled in autofocus with the fact that I think GitHub doesn't have quite the right like paradigm for machine learning projects. So these version control systems are designed for projects where the code is the main thing. And for that code, you have like a central master branch that's more or less evolving linearly over time. Sure, sometimes you revert or whatever, but for the most part, you're like adding features and doing bug fixes, and like the new code replaces the old code. Machine learning projects really aren't like that. They revolve much more around data and experiments rather than code. Of course, we're writing code as we do our experiments, but the more interesting thing is like the model you get out in the end and what was its performance. And the code is kind of incidental. But the whole thing revolves around like a data set and what you're trying to predict for that data set. And also the way the code evolves is often not like a linear progression over time. So one set of experiments might evolve linearly over time, but then when you do a second set of experiments, that just kind of exists in like a parallel world with the first set. You probably want to keep both sets of experiments around, especially if like the first produced a model that's in production, you want to still have the code that produced it. And so you have these like parallel worlds rather than like one central code base that's evolving forward. So one step towards solving this problem is to localize it by separating libraries from apps from your workspace where you're developing your models. For autofocus, for instance, the creevey library actually kind of grew out of autofocus. So as I was writing code to process the autofocus data, and then writing a lot of the same code at ShopRunner for the work I was doing there, eventually I realized like, hang on, there's a common pattern here. If we made a framework to handle those common patterns and made that into its own library, that would save us a lot of work. So we pulled out that code into a library. We also have an app inside autofocus that serves predictions from the model. And then alongside that, we have the code that we use to train the model. So I found it very helpful to separate these things out, be clear about which one is which, and instead of having them all like together in one big blob. So to help maybe clarify some of these terms, when I'm talking about a library, that would be a package that you install and import. So it'd be code that's useful across multiple projects. So like pandas, scikit-learn, pytorch, creevey, these are all libraries. This code fits quite well into the GitHub paradigm. Right, the code's the central thing and it evolves forward over time. Ideally, a library would be coherent. It would do like one sort of thing, like creevey does file processing pipelines. But at your company, you may have like a grab bag or two library with stuff like database connections.
Hey, Greg.
Yep.
So Google's pretty famous for using a monorepo, and I was wondering if what you're describing is in line with that. I suppose it works well for them because they've done a lot of work in ML.
Yeah, so jumping ahead, you have options for, so I say you should separate these components, but that doesn't necessarily mean they have to be separate repos. I tend to favor putting them in separate repos, but you can also have, like make the separation into different directories within a repo.
Cool.
Okay, so libraries are these things that you use across multiple projects. An app then is like the end of the line. This is the code that you run directly. So for instance, a Flask app that serves your model predictions. And again, this code fits well into the GitHub paradigm. And again, right, so options, you have options for how you separate out these components. Again, I tend to favor separate repos because I think that makes the distinctions really clear. You get really clean lines between these things. It's easy to say like, creevey is a library, it's not an app, and so on. But other people don't like having all of these different repos that they have to keep track of. So it also makes sense to put closely related code into a single repo, just with different directories. So autofocus is actually set up this way, where we have a predict directory that has the app for serving predictions, and then a train model directory, which is where we put the code for training models. Okay, so that's right. So again, we started with this problem that machine learning code doesn't really fit all that well into like the GitHub paradigm. So step one to addressing that problem is to localize it. So to separate out your machine learning code from other kinds of code. But now we still have the machine learning code to deal with. My suggestion here is, if possible, don't use GitHub or whatever. Use something like Kaggle. So Kaggle, I think, has like the right model for machine learning projects, where it has data sets, and associated with a particular data set, you have like notebooks with people's experiments and discussion and so on. So it all revolves around data sets. And different experiments, right? It's not like a single code base that sort of forces you to evolve it over time. You have different experiments that just live in parallel, like in this notebook section. Problem with that is it's not always an option. There's not like a Kaggle enterprise, or there are some machine learning platforms that maybe look somewhat like this, but there's not like one widely adopted platform that follows this kind of approach in the same way that like GitHub Enterprise or Bitbucket is. Any tech company is going to have something along those lines. So you might be stuck with a standard version control system. So if necessary, you would need to adapt that to the machine learning domain. But again, your project revolves around data, so you should put that front and center. So put simple instructions for retrieving data, I would say in the README, make it as visible as possible. I found it helpful to provide at least 3 versions of the data. So you probably want to provide the rawest data that you have. So like for autofocus, this would be the original images without any of that processing for people who really want to get their hands dirty. Second, provide lightly processed data, which like try to stick to processing steps that you think it's reasonable to assume that anybody would want to do. So for the autofocus data, I do trim those bottom 100 pixels or whatever, and then resize them down to be 512 on the shorter side. I think most anyone who's going to work with that data will want that. So most people coming to this project will want the lightly processed data. In addition, people may want to get just a small sample of data to see what it looks like and play around with it. So I think it's nice to provide a sample data set that's, say, less than a gigabyte. So here's what that looks like on autofocus. So we have these instructions where you create an environment variable, again, specifying where you want the data to live. And then we have commands that refer to that environment variable to download the data as like a zip file, unzip it, and then get rid of the zip file. Okay. So that's a way to make the data set very prominent in your machine learning project on GitHub. I said you want to provide lightly processed data as well as the original data. There's probably have some code that you use to do that. So you'll want to have a place where that code lives. So for autofocus, for instance, we have, let me start here, right? Alongside the app that serves predictions and the directory where we develop the models, there's this build dataset directory that has the code that was used to process the data. Okay, and then in addition, again, you're going to have this space where you do your model training. Within that space, I would give each set of experiments its own self-contained subdirectory with its own README, requirements.txt, Docker files, and so on. Right? This isn't code that evolves linearly and the new code replaces the old code. When you start a new experiment, it's really like a whole new thing. It should probably have its own, be its own like self-contained directory. So like in autofocus, in the train model directory, we have these directories named for the month when we started working on them. Okay, so we'll move now from managing code to managing dependencies. Are there any questions before we get into that topic? Okay, there's this dilemma in like any software project on like how many of your dependencies do you pin precise versions for. So if you want your code to run in a totally reproducible way, that requires pinning down exact versions of all of your dependencies. But then when you want to add a new dependency or update a dependency, that can be really annoying because a lot of these frozen versions won't be compatible. And then you're also missing out on updates to these libraries, which might include not only new features and performance improvements, but also security patches that are quite important to have in place. So what should you do, right? Should you do this thing on the left where you have the lightly, so these are like just the direct requirements with things pinned only where necessary, or this thing on the right where you pin everything. So we found that there's a tool called pip-tools that we're using at ShopRunner that gives you a lot of the best of both worlds. So pip-tools allows you to write the thing on the left with the lightly specified dependencies. So they're sometimes called abstract requirements. So like your direct dependencies with as little pinning as possible. So that's what you write. And then this thing's easy to update if you want to add a library or you need to pin something. There's no problem. And then pip-tools gives you a command called pip-compile that will compile your abstract requirements into fully specified concrete requirements. So it'll generate a requirements.txt with this full set of totally pinned down dependencies with comments telling you where the indirect dependencies are coming from. So now you have the best of both worlds, right? You get to write the simpler thing that's easier to update. When you need to upgrade these dependencies, you just run pip-compile again, and then you get this fully specified thing that, you know, as long as you test it, you can ensure that, right, this set of dependencies will work. pip-tools also gives you a second command called pip-sync, which ensures that your environment has exactly this set of libraries in it, what's in your requirements.txt. So normally you would do like pip-install from your requirements.txt, and then it would install those libraries on top of whatever you already have. If you do pip-sync, it wipes out everything else, so you just have exactly what's in your requirements.txt, which helps, again, ensure that your work is reproducible. If you're using pip-tools, we found it helpful to set up hooks to make sure that we keep things up to date. Right, so there is a potential issue, or like a question with pip-tools of like, how often do I recompile these concrete requirements? And the solution we've come to is we set up this pre-push hook, which, so what this does is when you're going to push your code to GitHub, it will check whether your requirements.in has changed. So this is the thing you write with your abstract dependencies. So your loosely specified requirements. If that has changed, then the hook will run pip-compile to get your requirements.txt with all the pinned down dependencies. And if the result is different from what's in your requirements.txt, it will fail your push and force you to compile your requirements again. So the details here are important. We make it a pre-push hook instead of a pre-commit hook. Right, so pre-commit hook would run every time you commit your code. A pre-push waits until you try to push it. And we do that because the compilation process takes several seconds to run. Like it's not minutes, it's seconds, but it's long enough that it would be a little bit annoying to do every time you commit. And also it only runs, we decided to run it only when the requirements.in has changed, right? Because at that point you have to recompile if your direct requirements have changed. You could set up like recompile every time you push, but that's probably too aggressive in updating your dependencies. Pip-compile protects you against having incompatible requirements, but it doesn't protect you against breaking changes. So if you're recompiling all the time, then like when pandas goes to version 1.0, if that breaks any of your code, then you have a problem. So I think this is a good, like a reasonable like frequency to update your dependencies. You're not doing it all the time, but you're forced to do it anytime your direct dependencies have changed. One issue we've run into is sometimes you have conflicts in your dependencies that cannot be resolved. We've seen this in particular with Bodo dependencies. There are things that depend on Bodo, which is like an Amazon AWS thing, like for talking to S3 and other services. We have a bunch of dependencies that can't always agree on what version of Bodo core to use. In some cases, we've been able to resolve this issue by like downgrading Bodo 3. So in that case, there was a solution, there was a consistent set of dependencies, but pip-compile wasn't able to find it and needed a little bit of help. In other cases, there just is no solution, and yet our code runs. So either there is some case where we'd have an actual problem because of incompatibility, or one of our dependencies was overly aggressive about pinning. But in any case, pip-compile couldn't find a solution. But I wanted all of the dependencies that were generating the problem. So in that case, I fell back to not using pip-tools, just write my abstract requirements. So with things pinned only where necessary. But then I did you can run the command pip freeze, which will print out all of everything that's installed in your Python environment. So as a fallback option, you can run that command and write the results to a file. And then you do at least have a record of a set of dependencies that worked for you. So it's definitely less elegant, but it still gives you reproducibility. A couple other tips for dependency management. So pip-tools will help ensure that your Python environment is like frozen so that you won't have failures of reproducibility from those libraries, but it doesn't do anything about the rest of your environment, like the operating system or any system libraries. So that's where Docker comes in. You can use Docker to freeze all of that stuff. However, Docker doesn't necessarily play nicely with GPUs, which you probably want for a deep learning project. But NVIDIA has its own nvidia-docker tool that ensures that the GPU is available inside your Docker container. So you can use nvidia-docker with the GPU. That'll be pre-installed on a lot of, like if you're using EC2 on AWS, a lot of the deep learning AMIs that are out there will have nvidia-docker already installed. Also, I said, right, it's nice to pin things down only when you have to. One thing I would definitely pin down is PyTorch or TensorFlow or whatever like framework you're using for deep learning. PyTorch at least is the one I use the most, and if you don't pin down the exact version, you may find that the model you saved last week, you can no longer load back in because PyTorch made a breaking change in like the architecture of the model, or just what something is called or something like that. So you want to pin down exact versions to ensure you can load back in what you export. It can also be nice to install these kinds of dependencies if you're using Docker early on in the Docker build. So like in this example, I'm installing Torch and related dependencies very early, and then later on I install the other requirements. And that's because Docker caches each of these steps. So if something changes down here, like down at the bottom, I copy some files into the container. If I rebuild my container and all that I've changed some of those files that get copied, then it'll rerun that copy step, but it won't go back and redo this installation. And this installation can take a while. So, right, in general, anything that is slow and is not going to change much, it's nice to put at the top of your Docker file. Okay, any questions on that section on managing dependencies?
Nope.
All right, then finally, managing experiments. So anyone who's done any machine learning, I think, can relate to, like, it's just hard to keep track of. As soon as you've tried two things, it's hard to keep track of like which thing gave you which results. So it's important to track your experiments. As much as possible, it's good to automate this process. So we've used mlflow tracking, which can log anything you want, but it's usually used for like hyperparameters and metrics. And then it records your history, like when you ran the experiment, and then whatever parameters and metrics you told it to log. It's really easy to use. Like in your code, you just import mlflow, and then you say like mlflow.log param, and you give it a dictionary with like the name of the parameter and the value. At ShopRunner, we use Databricks, so we write all of these logs to Databricks, and we can view them there. But you don't have to have Databricks. You can just write it all locally, or there are lots of options for where the data goes and how you view it. But in my experience, and whenever I've tried to do something with mlflow, it's been quite easy. So that's like one side is anything that you know you're going to want to record, just automate that, and then you don't have to think about it. There's also going to be like more informal observations, things that come up along the way. I found it really helpful to keep like a lab notebook where I record this sort of thing. And it doesn't have to be anything fancy. I just use a Google Doc and just write down like the date and the time, and then anything that, like any observations that I want to jot down and maybe think about later. There have been cases where like I had an error that I know I've seen before, and I just did a Control F in my lab notebook, and then I was able to find it and my notes on how I solved it. Okay, so we're coming to the end, so let me summarize. We have this creevey library that's been really helpful for us processing large collections of files. Machine learning projects are different from other software projects. It's helpful to organize them accordingly. So I like to separate libraries and apps from the model development materials. Within those model development materials, organize them around the data more than around the code. For that code, have separate little mini self-contained little workspaces for different versions of the model. pip-tools is helpful for managing your dependencies, and having a lab notebook and something like mlflow is helpful for tracking experiments. But wait, there's more. Keep an eye out for ShopRunner is soon going to be releasing a library called Tonks, which is for training deep learning models that have multiple inputs and or multiple outputs. So for us, we have products where we have both images and text, and then we need to classify them in different ways. For instance, with regard to the pattern of the shirt in this case, and also the sleeve length. So if you have problems like this, maybe you have both images and text and you want to do some classification, and or you want to do like multi-label classification, keep an eye out for that. Thanks to the ShopRunner data science team for feedback, and especially to Nate Jones for his meme contributions. Couldn't have done it without you, Nate. All right, thank you very much. I'd be happy to take additional questions or just chat.
Thank you.
Now I understand Nate's comment. in the chat.
Thank you.
I thought it was an excellent meme. I agreed with it, but now I actually understand why you put that there.
Thank you.
So is anyone running something similar, sort of in production? The context of all this is, of course, doing machine learning and deep learning in a production context where it's easy to make a little mistake in detail and get different results in production when you didn't mean to. So this topic of library management, dependency management, and sort of keeping track of every little thing is a very common paradigm in software engineering contexts. Not so common in traditional data science contexts where you're kind of working through a notebook and running through some transformations and trying to get the math right. But spinning that out into a production context is, as you can see, quite a bit different and quite involved. Is anyone else doing this sort of thing in their environment?
I was planning on using weights and biases, and it's a product just for commercial or production, and that was recommended in a there was a COVID-19 contest, and that's what they were using. And so if you go to wandb.com, that's the link for that.
Nice, yeah. So I said like there's no Kaggle Enterprise or like machine learning, no like widely adopted machine learning project management platform that has anything like the mind share of like GitHub, but there are certainly a lot of platforms springing up, and some of one or more of them might be the right thing. Just hasn't totally caught on yet.
Hi, I had a question. I was wondering if you had any tool recommendations around just optimizing and tuning hyperparameters. Like if you wanted to do grid search or Bayesian or something else random. What do you use for that?
Yeah, I'll throw that out to the room. I'm not sure I'm sure others have probably better answers than I do.
Guild. I've used Guild AI to optimize to find the best hyperparameters on projects. I'll drop the link in the chat.
Great, thank you.
And then also AutoSKlearn if you're doing just straight machine learning as an attempt to find something brute forcey.
Thank you, that's helpful.
Yeah, so I'm a fan of the Fast AI library, which claims to have really good defaults and has like an interactive way to find a good learning rate. So I tend to do less like brute forcey kind of hyperparameter search. Our team looked at Determined AI has a tool that's a platform that's really quite good for hyperparameter search.
Thank you.
Any other questions for Greg? Okay, in the interest of keeping the recording short, I'm going to stop that, and but we can stay on. People who want to stay on and chat about anything else, feel free. Let me figure out how to stop this. There we go. All right, we're officially stopping the recording.